Assalamu alaikum. Myself, Dr. Ansari Farzana, Department of Chemistry, J.A.T.rts Science and Commerce College for Women. Welcome all of you. In the previous section, we have seen that the phase diagram for water and carbon dioxide. Today we shall discuss about the phase diagram of sulfur system. The phase diagram of this system is complicated due to the existence of sulfur in two crystalline forms, namely rhombic sulfur and monoclinic sulfur. The sulfur thus exhibit allotropy. The phase diagram is shown in this figure. Okay, this figure is very complicated. See the diagram. Screenshot this diagram. Then we shall discuss about this diagram one by one in detail. The diagram is divided into 4 areas, each containing single phase within the specified range of temperature and pressure. Within the area, the system is bivariant. F is equal to C minus P plus 2. That means it is equal to 1 minus 1 plus 2. That means is equal to 2. Both the pressure and temperature must be specified in order to describe the system completely. To the left of the curve OPSW, rhombic form of the sulfur exists in the system. OPSW. See here, OPSW. This is the W. This is OPSW. Rhombic form of the sulfur exists in area OPSW. Below the curve OPKQ, sulfur exists in vapor state in the area bounded by the dashed line at T0, the critical temperature of sulfur. Above this temperature, sulfur exists only in the vapor phase. There are 6 curves representing the true equilibrium, 3 representing the metastable equilibrium. Along the curve, 2 phases coexist in equilibrium, and according to the phase rule, F is equal to 1 minus 2 plus 2. Minus 2 plus 2 gets cancelled, then F is equal to 1. The system is now monovariant. To describe the system completely along the curve, the pressure or temperature is specified, the other automatically gets fixed. The curve OP. Along the curve equilibrium, rhombic sulfur vapor exists. The curve is sublimation curve for rhombic sulfur. Curve PK. The curve is sublimation curve for monoclinic sulfur. Along the curve, monoclinic sulfur exists in equilibrium with sulfur vapor. Monoclinic sulfur vapor when the temperature of monoclinic sulfur is raised slowly at 1 atmosphere pressure at 95.5 degrees C, it gets converted into monoclinic sulfur. P is called as the transition point. Likewise, when the temperature of the monoclinic sulfur is slowly lowered, it gets converted into rhombic sulfur at 95.6 degrees C. The transition from rhombic sulfur to monoclinic sulfur is thus reversible. Crystalline forms that undergo reversible changes, monoclinic sulfur and monoclinic sulfur, are said to be enantiotropic, and phenomena is called as enantiotropy. It is derived from the Greek word meaning opposite change. curve KU. KU, that means this curve see here, curve KU. KU. At point K, 120 degrees C, monoclinic sulfur melt. Along the curve KU, liquid sulfur coexists in equilibrium with its vapor. The curve represents the variation of vapor pressure of liquid sulfur with temperature. Temperature at U, that means Tc, is called as critical temperature for sulfur. Above this temperature, sulfur exists only in vapor form, whatever may be the pressure. Line PS. In the curve, line PS curve represents the variation of transition temperature of rhombic sulfur into monoclinic sulfur with pressure. Along the curve, the two forms coexist in a state of equilibrium. As pressure rises, the transition temperature shifts to higher temperature. The curve Ks, that means line Ks, represent the variation of melting point of monoclinic sulfur with pressure. Increase in pressure also raise the melting point, but the increase in transition temperature per unit rise in pressure is more than the corresponding rise in the melting point of monoclinic sulfur. The two curves therefore intersect at point S. Along the curve, the monoclinic sulfur coexists in equilibrium with liquid sulfur. The point in the line SW, the point S rhombic sulfur melts, and along the curve rhombic sulfur coexists in a state of equilibrium with liquid sulfur. The dotted line PR, if the temperature is raised rapidly beyond to 5.6 degrees C, the rhombic sulfur exists in rhombic form. Without its conversion into monoclinic form, the line PR is the equilibrium line for superheated rhombic sulfur with sulfur vapor. The dotted RK line represents the supercooled liquid sulfur along the extension of UK to point R. At point R, the metastable rhombic is in equilibrium with sulfur vapor. Sulfur vapor line is intersect the metastable sulfur liquid sulfur vapor line to yield the metastable point. Rhombic sulfur is in equilibrium with sulfur liquid is in equilibrium with vapor. The dotted line RS show the variation of metastable point. Rhombic sulfur in is equilibrium with liquid sulfur is in equilibrium with vapor sulfur with pressure and is therefore the melting point line for rhombic sulfur as function of pressure. This line is an extension of a stable WS line into the metastable range. When this variation metastable equilibria occur, monoclinic sulfur does not appear. Instead, rhombic sulfur is the transformed directly to liquid along RS to vapor along with PR without passing through the monoclinic stage. Triple point. The diagram contains three triple points at P, K and S involving true equilibria and one point R involving the metastable equilibrium. At all these points, three phases coexist in equilibrium and the system becomes invariant. Point P, following 3 points coexist at equilibrium. Rhombic sulfur is in equilibrium with monoclinic sulfur is in equilibrium with sulfur vapor. As long as the three phases exist in system, the temperature and pressure of the system will not change. At a constant pressure, if the attempt is made to increase the temperature of system, more of the rhombic form will be converted into monoclinic form. The supplied heat will be utilized in the conversion and temperature of the system will remain constant. Once this conversion is complete, the system will contain two phases, namely monoclinic sulfur and sulfur vapor. The temperature of system will begins to increase and it will move along with curve pk. The point K following three phases at the point K following three phases coexist in equilibrium. That means monoclinic sulfur is in equilibrium with liquid sulfur is in equilibrium with sulfur vapor. At point S, three phases exist as rhombic sulfur is in equilibrium with monoclinic sulfur is in equilibrium with liquid sulfur. At point R, the following three phases are obtained. Rhombic sulfur is an equilibrium with liquid sulfur is an equilibrium with sulfur vapor. Both temperature and pressure of the system will remain constant as long as three phases coexist. When one of the phase disappear, temperature or pressure of the system will change and further the curve represents the equilibrium between the remaining two phases. Note down that if monoclinic form of sulfur would have been non-existent, a phase diagram similar to that of water system would have obtained. This is the simple application of phase diagram and sulfur system at a glance. Area to left OPSW rhombic sulfur, then at area OPQ sulfur vapor, etc. and etc. are obtained. Thank you for watching.